This video is going to discuss simple harmonic motion. Students will be able to cite the equations and properties of simple harmonic motion after completing this video. So what is simple harmonic motion? Simple harmonic motion, usually abbreviated as SHM, is defined as a type of periodic motion where the restoring force is directly proportional to the displacement and acts in the opposite direction to that of the displacement. Since those words probably don't mean a whole lot to you yet, just take my word for it and we'll see some examples. One example is a pendulum, so let's look at that one first. The simple pendulum consists of a mass suspended from something, a string or a rod or something, and it's allowed to swing back and forth or oscillate. The initial rest position is in the middle and it's called the equilibrium position. The angle of displacement from equilibrium is called the amplitude. So let's talk about the period of a pendulum. Period is the time it takes for it to complete one oscillation. So let go from rest, swing to the other side, and come back. So when it comes back to its original position, that was one oscillation, and the period would be the time it took to do that. The period of a pendulum only depends on the length of the pendulum and the strength of the gravitational attraction that whatever gravitational field it's in. In this case, usually on Earth, we'd use 9.81 for G. Where T stands for the period, measured in seconds, L stands for length, measured in meters, and G is the acceleration due to the gravitational field. Like I said, usually 9.81 meters per second squared, or 10. That's a big square root there, so the L and G are both inside the square root, and that matters. Let's talk about the relationship between frequency and period. Frequency is defined as the number of oscillations per second and is measured in hertz, which is abbreviated as Hc, or seconds to the -1, which means per second. Frequency and period are both related to angular speed from that circular motion stuff I talked about before. Frequency is inversely proportional to period, which means as one goes up, the other goes down. So here's the equation that's on the AP equation sheet that relates period, frequency, and angular speed. So as frequency increases, period decreases, and vice versa. Now let's talk about the other example, masses on springs. We talked about this before when we discussed Hooke's law, and we know that the force a mass feels from a spring depends on the spring constant of the spring and the displacement of the mass from equilibrium, or F equals kx, which is Hooke's law. X can also be called the amplitude in this situation. So we can use A or X here for amplitude. The period, if this mass is allowed to oscillate back and forth from equilibrium, then it's undergoing simple harmonic motion. And its period of oscillation back and forth only would depend on the amount of mass present and how stiff the spring is, or its spring constant, in other words. So the equation for the period of a spring undergoing simple harmonic motion is 2 pi times the square root of the mass divided by the spring constant. So Ts is the period of the system, measured in seconds, M is the mass, measured in kilograms, K is the spring constant, measured in newtons per meter. And generally speaking, the more the mass, the higher the period, so the longer it takes, and the larger K gets, you're dividing by a bigger number, so then the period would decrease. So if the spring is harder and stiffer and harder to depress and stretch, then the period is going to be very short. So it'll oscillate very quickly. And we can also relate this to conservation of energy. Generally, the larger the amplitude for any system undergoing simple harmonic motion, the greater the potential energy. So when a spring is at its maximum displacement from equilibrium, that's when that mass has its greatest potential energy and therefore lowest kinetic energy. That's what this little graph is showing. When the kinetic energy is greatest up here, the potential energy is the least. And that's when it's in equilibrium. When at greatest displacement or greatest amplitude, the kinetic energy would be nothing because it's going to stop there when it changes direction, so it'll have no speed. And that's when the potential energy is greatest. This happens on the other side when it oscillates back and forth and back So for example, a spring pulled as far as possible from equilibrium position will have maximum potential. When passing through equilibrium, that's when the speed is the greatest, and that's when the kinetic energy would be at a maximum, and the potential energy would be at a minimum. There's a whole lot of stuff going on in this picture. So if we imagine this mass being suspended from this spring vertically and being pushed up, now it feels a force downward from the spring toward equilibrium. So the force will always be directed toward equilibrium. In this situation, the velocity is 0 because it's basically changing directions at this point. Here, the mass is right at the equilibrium position, so this is when its velocity is at a maximum. And this is also when there's no net force. It's no longer accelerating. After it goes past equilibrium, now it's slowing down and stopping at this maximum displacement point. So this is where the potential energy is the greatest again, and the velocity is 0. Then it goes back. So it's basically the same thing. And this keeps happening over and over and over again until external work done by friction and heat and sound takes enough energy out of the system so that the mass stops. And finally, let's talk about the sinusoidal nature of simple harmonic motion. So imagine a spring undergoing simple harmonic motion, oscillating up and down, as a roll of paper moves by, sort of like this picture over here. The position of the mass and spring would produce a sine wave function as shown on the picture. So as this mass swings up and down, if you imagine it drawing on the paper, it would make this kind of sine wave looking thing. We can get some useful information from that wave. If we use x as the position, in this case the vertical position of the mass, you can see the x, it's x and negative x over here on the y-axis, which is kind of odd. That can equal the amplitude, so how high up it goes from equilibrium, times the cosine of all this stuff, 2 pi the frequency times the time. So if we know what the frequency is, and we know what the amplitude is, then we can figure out the time it would take to do an oscillation. We can use this information to find things. That's it for this video. Thanks for watching. Remember to bring your notes to class to help on the note quiz.